Gnanam paramam dheyam. Knowledge is supreme.
Alright, so in the last lecture we saw how one uses a discriminant to compute the nature of the Galois group, and now I will give without proof how does one compute the discriminant without knowing the roots of the polynomial. So start with the polynomial f, monic. F is a monic polynomial, x power n plus n minus 1 x power n minus 1 plus a1x plus a0. This is a polynomial with coefficients in k, and we don't need to assume f is irreducible, so arbitrary monic polynomial, and our goal is to compute discriminant of f, and we know definitely this is in k. That is because it is the symmetric in, so we have checked that this polynomial is symmetric polynomial, and therefore it is a polynomial in elementary symmetric functions, and elementary symmetric functions of the roots are precisely these coefficients. Therefore that's how we have concluded that it is in k, because this is in k, and so we want to compute this constant, and if it is 0, we know this polynomial, this discriminant is 0 if and only if f has a multiple 0. In fact, we know the formula for the discriminant, that is in terms of the roots, that is discriminant of f equal to van der Mode x1 to xn square. This van der Mode is product 1 less equal to I less than j less equal to n xi minus xj whole square. So if you want to compute this, it is a horrendous job, because given a polynomial of very high degree, it will be nearly impossible to compute all the zeros. Okay, so here is the recipe. You have the polynomial f, monic, that I have already written, and we have this kx, and go mod ideal generated by f. Then I get a vector space. This is a k vector space, and the division algorithm will tell you this k vector space is finite dimensional. In fact, the dimension of this vector space, dimension of this, dimension of as a k vector space of this kx mod f ideal generated by f, this dimension equal to the degree of f. And what is the basis? In fact, the basis you can write down. Take the small x, let small x be the image of capital X in this residue ring in kx mod f, and the basis is then 1 x x power n minus 1. This is the basis where the degree is n. That is clear. This is how you use the division algorithm. If you have given any any element here will be a polynomial mod f, but that polynomial, after dividing by this monic polynomial f, I can assume it is degree less equal to n minus 1, and read that mod f means replace capital X by small x, and then you get a linear combination of these guys, and this is unique because the division algorithm is unique. Therefore, this is a basis. Okay, once this is a basis, remember for any y, let me call this as v, not v, let us call this as b. This B is a finite dimensional K vector space, and this is the basis. This is a K basis of B. This is what I will use it. Now, given any element y in B, you look at the multiplication from the left by that y, lambda y. This is B to B. Any element G going to y times G. This is clearly a clear linear map of the vector spaces, and therefore determinant of that makes sense. Determinant of y, this makes sense, and the determinant will therefore be an element in K. And this is how many cross how many determinant? This will be n cross n determinant. So this is also one denote this is a norm of B over K of the element y. So let me write it on the next page. So norm B over K of y, this is the determinant of the linear map lambda y. So this norm, we have said earlier also, norm of B over K, this is a map from B to K, and it is multiplicative map. So first of all, the properties it satisfies is norm of Bk. If I take any constant, any a, this is a power n, and norm of this y times z is norm of b over k y times norm of b k over z. This is trivial because determinant is multiplicative. Determinant of a times b equal to determinant a times determinant b. Therefore, this is clear, and also it is clear that if y is a unit in B, if and only if norm y is a unit, norm y is a unit, but norm y is an element in K, its unit in K means it's a non-zero constant. So, and this norm is also used to study some special properties of the B, namely what are the units, what are the, and so on. So, I will not go too much into this. Now, I want to write down a formula for the discriminant in terms of this norm. So, we have given f, monic degree n, monic of degree n, then from the f, degree n, degree of f equal to n. From here you go to the residue class ring B, which is kx mod f, and let us take an element, we have given f, so we can differentiate it. Differentiating is not a big problem. So this is d dx of f, formal derivative of f. And now read f in this ring, that is, take the image of f in the ring B, but that is what? You take this derivative and plug in instead of capital X small x. So f prime small x. This is an element in B. So this is my y. And compute the norm of f prime x. And this is nothing but the discriminant. Or maybe I have to see the sign plus minus. So this is the discriminant of f. This is a nice formula. This is how we compute. So, for example, if you wanted to compute cubic discriminant, then this f prime will be degree 2, and finding a norm of degree 2 will not be so difficult because it's a degree 2 polynomial, and then only the matrix involved will be 3 by 3, and therefore this is computable, and this doesn't require the knowledge of the zeros of f. So this is how one computes effectively in fact this way you can use it even, you can write down some small software in using some computer algebra packages, you give f and then they'll give you the discriminant. and then testing whether it is square or not, etc. Also, discriminant has another nice formula. So, but that again involves the roots, but it is a nice formula. Discriminant of f is the product is running over J, and you take f primes and evaluate the roots xj. So, this is running over the roots of f. So, this is v of f equal to x1 to xn. And this does not even require the fact that, so it is visible here, if it has a repeated root, then f prime will be 0 at somebody, and therefore this side is 0. And this is again plus minus sign. So that one can determine the sign just from the determinant side, so on. So I will not spend more time on the discriminant anymore. That is way to compute, and one can do the computation for small degree polynomial, degree 3, degree 4 certainly one can possible, because you can compute the determinant of degree 3, order 3 and order 4. Alright. Now I want to say something more about the cyclic extensions. Cyclic extensions. I want to list all cyclic extensions, but this I will do it almost with a proof, but the details, some of the details I will leave it. For example, suppose I assume, so we will assume here, we assume that my base field K contains roots of unity. If necessary, I will replace K by K and adjoin all the roots of unity. For example, in characteristic 0, you apply this, attach all the roots of unity in C. It's a group. It's a big group, and you don't need so much. You attach nth roots of unity. This is a finite group, finite cyclic group, and attach that. So you still get a finite extension. Alright. So I will assume that it contains roots of unity. We don't need all nth roots of unity, and that n will depend on the degree, etc. So assume that, and suppose that this x power n minus a, this is a polynomial in Kx, and it is separable and irreducible. That means what? What condition one needs to put is characteristic should not be divisible by n, p should not divide n. This is characteristic of K. And separability will be that, and irreducibility is another thing to check, when will such a polynomial be irreducible. But assume that, then under this assumption, then the Galois group over K of this polynomial is cyclic of order n. In fact, I will give an isomorphism. So, in fact, the map from Galois group of x power n a, n minus a, to where? Cyclic group, I need a cyclic group of order n, and who can be better than mu n k? This is cyclic of order n, and we are assuming this is contained in K, no? All nth roots of unity are lying in K. So this is cyclic of order n, and I want to give you a map first. So take any sigma and map it where? And fix any root. Let x be any 0 of x power n minus a in the splitting field, of course. X any, fix that, and map this sigma to sigma x by x. x, first of all, x cannot be 0 because it's a root of this, and a is non-zero of course because it's an irreducible polynomial. So look at this map. First of all, this map doesn't depend on x, and this map is an isomorphism. So that proves that the Galois group of this polynomial is cyclic. So that means this extension splitting field of, so that means this is cyclic. Gal k x power n minus a is cyclic. So that means also we are saying that no, L over k is cyclic extension. So this map is canonical because it doesn't depend on the choice of x. So this is a canonical group homomorphism. Canonical group isomorphism. It is clear that this is the nth root of unity because you see you raise it to n. When you raise this to n, what will it be? This is sigma of x power n, this is x here, no? Divided by x power n. But x power n is a, and sigma of x power n will be sigma x whole power n. This is sigma, so this is 1. Right? So therefore this map is indeed a map here. It is clear that it is a group homomorphism, and it is also clear that it doesn't depend on x. So it's canonical. Okay. And conversely, what does that mean? And conversely means given any cyclic extension where the base field contains cyclic extension of degree n, where the base field contains nth roots of unity, then there exists a polynomial x power n minus a such that this L is a splitting field of x power n minus a. So that characterizes all cyclic extensions. And this was multiplicative. Similarly, one can do it additively, but I will not do it now because we are running out of time. And now I will only state two important results due to Schur, which are difficult to prove and it will require quite a bit effort. But maybe it is a good way for studying further. One wants to study more. So this is Schur. All right. So you look at the exponential series e power x. This is 1 plus x plus so on, x power n factorial by n factorial and so on. And now I want to make a polynomial. So I should only consider up to here. And that I will call it En. En, this is a polynomial. This is a polynomial in Qx. Degree of En is n. The problem is to compute the Galois group of this over Q. So, what is Gal Q En? When I say what is, that means how can you describe this Galois group in terms of the known groups? And the answer is very nice, but not so easy to prove. Alright, so I will tell you the answer. So, I will list some of the facts according to their difficulties. So, first of all, note that En has exactly one real zero if n is odd, and no real zero if n is even. Secondly, check that En is irreducible over Q. And remember here, Eisenstein will not help. Eisenstein criterion may not be helpful. It is helpful only up to I think n equal to 6. It is helpful because when n grows, when you clear the denominator n factorial has many square divisors, so it may not help. Now then the third important thing is, what is the relation between En and En plus 1? The relation is, if I differentiate En plus 1, you get En. This is easy, of course, this I should have said in the beginning. So, these are irreducibility is difficult. Alright. So, now the result, this is sure. He has computed the Galois group and says Galois group of En over Q is Sn if n is odd and An if n is even. And this requires quite a bit of a proof, so I will not indicate the proof here. And once you do this, then you can do many more examples where the Galois group is Sn or An. Once you have this, then also you can try to see when the other groups, how do you compute, how do you write down polynomials whose Galois group is this. For example, Dn is a dihedral group, or what is Klein 4 group. Klein 4 is simple because it is order 4 degree, or what is that, quaternion group. So, the quaternion group plus minus 1 plus minus I plus minus j plus minus k, this quaternion group is also order 8 group. This is non-abelian group, and you will, what equation will you write down whose Galois group is this, what equation will you write down this Galois, and so on. So, when one wants to study Galois theory more later, you have to devise a method. How do you find a polynomial of the primitive element, minimal polynomial of the primitive element which describe the field extension. And this minimal polynomial also called Galois resultant, or primitive element is also called Galois resultant. These are the terms used by Jordan and people later who tried to study Galois theory much more intimate way. And also one can do much more this, but then the methods will be used from the other subjects, especially algebraic geometry, algebraic curves, or more from complex analysis side, or more from algebraic topology, that computation of fundamental groups of a topological space is closely related to the computation of the Galois groups and so on. So, with this I will stop here, and I hope you have enjoyed this course very much. I tried to keep the prerequisite as less as possible, but because of that probably I cannot go on more because the time constraint. So, thank you very much for your attention.